All right, welcome back to The Effect. We're going to be closing out Chapter 13 on regression here by talking about Probit and Logit models. So far we've been working with linear regression. We assume a linear relationship between our predictors and our outcomes. Now sometimes we do some sort of transformations to allow for some sort of weird kind of shapes. We talked about polynomials, we talked about logarithms, but sometimes this can't even be true. This still doesn't work. And what this has to do a lot with is the kind of dependent variable that we are predicting. We've been sort of making the sort of background assumption that the dependent variable that we're working with is sort of continuous, that it takes any sort of number of range, like not really restricted in terms of what it can be. And the basic ordinary least squares model assumes that that's what we're dealing with. However, that's not going to be the case in a lot of situations. There are a lot of dependent variables we might be interested in predicting that are simply not continuous. This can take a lot of forms. For example, maybe you have a variable that can only be you're counting up how many of times something happened. That can only be an integer, and it can't be negative as well. There's also a lot of variables that are continuous but can't be negative or can't be positive. One that comes up a lot, and the one that we're going to be focusing on in this video, is the case of binary dependent variables that can be only 0 or 1. And we talked about using these as predictors, but what happens when we use them as the thing we are trying to predict? And there are a lot of cases where this happens, right? We might be interested in what's the effective treatment on whether you got cured of your disease. Did you get cured? Yes or no. Did you make it into college? Yes or no. Did you move to a different house? Yes or no. There's lots of different outcomes we might be interested in that are binary in nature. Now that said, we're only going to be focusing on that one particular thing. We got binary outcomes. We're only going to be focusing on Probit and Logit. There is, in fact, a whole wide world out there of different kinds of models that you can run for different kinds of dependent variables. We're going to sort of skip through that in this book. That's not really what we focus on here. We're focusing on causal inference, but I am going to talk about Probit and Logit. So Probit and Logit regression are basically ways of doing the same thing we were already doing. We're using a set of predictors to predict some sort of outcome. But the only difference is that they make some adjustment to the prediction to make sure that it makes sense to predict a binary outcome. You can imagine why we might need to do this. So let's take a look at this graph right here. So this is showing an example of a binary outcome variable. You'll notice that all of the data points are either at 1 or at 0. Nothing in between, because the outcome that we're predicting can only be binary. Now you'll also see that we have an ordinary least squares line on there, and you can in fact run ordinary least squares when you have a binary dependent variable. This is what's called a linear probability model, because we are treating the probability of the outcome linearly. Right? Ordinary least squares is all about linear relationships, and so we're using a linear outcome. But there's a problem with this. So there's actually two problems with this. One is that you can see that the ordinary least squares line extends beyond 0 and 1. And that line is telling us what our prediction of the outcome is going to be. And so it's telling us that we're predicting for particular values of on the x-axis that the probability that the outcome is 1 is 110%, or 150%, or 3,000% if you go out far enough. Or it's -2, right? And those doesn't really make sense, right? You can't really have a probability that is between 0 and 1. And that's what ordinary least squares is trying to do when you have a binary outcome. It's trying to give you the probability that the outcome is equal to 1. So we get predictions that are outside of the bounds of possibility. That's one problem with using ordinary least squares. So what can we do about this? Well, you'll notice on this graph we also have a sort of curvy line there representing what we can do with Logit or perhaps a Probit model. And what is that doing? Well, it's using this, what's called a link function right here. So this is what's called a generalized linear model with a link function. So this is the equation we're looking at. And you can see some things we recognize, right? Inside of that f, what do we see? We see beta 0 plus beta 1 times x. That looks very similar to what we've been doing before. It's sort of just taking all of our predictors and adding them together with some coefficients in a linear manner, just as we've been doing with ordinary least squares. And in fact, that is exactly what it is. That's called the index function, that inside part. Beta 0 plus beta 1 times x is the index function. Now, the only difference between ordinary least squares and generalized linear models is that we take that link function, or we take that index function, we run it through what's called a link function, and that's the f right there. And what it does is it takes that index. Now, the index could be any value, right? If you make x a super big negative number, then that index is going to be really big and negative. If you make it a super positive number, it's going to be super big and positive. So that index can take any value in any range. So we need a function, a link function, that we can pass through something that takes any value and get out something that's in the same scale as our actual dependent variable. So we want to be able to put in any number and get out something that is between 0 and 1, because that was a problem we already had, right? That ordinary least squares is going to predict values outside the range of 0 and 1, when in fact our value has to be within that range. So that's where the logit and probit link functions come in. I'm not going to go into the math of this super deeply. In fact, for a lot of this video, you might want to read the textbook chapter for a lot more detail on exactly how to do all of this. But the idea is we take that index function, we pass it through a link function to get out a value that has to be between 0 and 1. And that gives us our probability that the outcome is equal to 1. The two functions are the logistic function and the probit function, where the probit function is the cumulative distribution function of the normal standard distribution, or standard normal distribution. So again, go back to the book if you're interested in more mathematical details on that. So by doing this, by taking the index function and passing it through a link function in order to get our prediction, it solves two problems. For one, we can't possibly predict outside the range of 0 to 1. Because whatever we're using this function for can't go beyond 1 and can't go below 0, then we can't go in our prediction above 1 or below 0. Great, problem solved. It also solves a different problem that linear probability models have. Let's go back to the graph. You'll notice that the logit model, it curves, right? It sort of curves to avoid the edges. What's going on there? Well, imagine that currently the probability that your outcome is equal to 1 is 50%, right? Let's say the outcome here is, do you go to college or not? And based on your background criteria, all the predictors I have for you, I'm going to predict that there's a 50% chance that you go to college, okay? So if I increase one of those predictors, maybe I give you some tutoring in high school, well, that can increase your probability of going to college, maybe from 50% to 55%, right? So that is describing the slope of our line here, right? I'm saying that I'm going to increase the amount of tutoring you have. It's going to increase your probability of going to college. We're going to move to the right on the x-axis and up a little bit on our line. But what if you're already pretty much guaranteed to go to college? What if you have a 99.999% chance of going to college? In fact, you are way to the right of this particular graph. And then I give you some more tutoring. Well, that might increase your probability of going to college a little bit, but you were already pretty much guaranteed, and you actually can't increase by 5% anymore. You were already at 99.9%. You just can't go that much higher, right? And so we would expect that, yeah, maybe it'll move the needle a little bit, but not a lot. Maybe it'll take you from 99.9% to 99.92%, right? Now, in that case, we see the exact same change on the x-axis, but a much smaller change in the probability of the outcome, which is telling us that near the middle, when you have a lot of room to move, we should see big effects. And when you are near the edges, when you're already sort of guaranteed to do something, there's simply not much more room to move. You can't increase any more than you're already at 99.9%. So we should see that the slope of the line should get flatter near the edges. Where there is no more room to move, we will do less moving. And the logit model does that. As we get near the edges, it flattens out. As it's near the middle, it's a lot steeper, like the ordinary least squares line is. And so the probit and logit models fix the problem of this sort of relationship here. That we're going to more accurately describe the relationship, because we're going to say that we're going to see bigger movements in the areas where we have more room to move, which is near the middle, when our predicted probability is closer to 50%, and less movement when it's near 0 or near 1. And in fact, the times when you want to be the most sure to use probit and logit, as opposed to an ordinary least squares or linear probability model, is if you think the probability of the outcomes is going to be closer to 100% or closer to 0%, as opposed to in the middle. Now, I should say that a lot of people will use ordinary least squares anyway. They'll use the linear probability model. And I think that there is actually, some benefit to that. Now, the probit and logit and other sorts of proper modeling of the dependent variable do solve some important problems. As I just mentioned, the predictions are going to be better, and the slope is going to more accurately account for where you are on the x-axis. But also it does introduce some difficulties, some computational difficulties. It has difficulties with things like fixed effects, which we'll talk about in a little bit. And so if all we're really interested in is the slope, then this sort of does solve that slope issue a little bit, but also, if it makes things difficult for us in some other way, they might not be worth it. So you can go back and forth on the argument of whether it's worth it to do probit and logit, and in what context it really matters to do. If you're not an economist, you're yelling at your screen right now because you're like, why would you not do probit and logit? We have a dependent variable model, or binary dependent variable. But economists do like linear probability models. I think there is some justification there. You can look in the book for a bit more detail on that argument. Now, one more thing to talk about with probit and logit models, which is how to interpret the results that we get. So it turns out you can't just look at a table of probit and logit coefficients and interpret them directly. It's very difficult to do. Instead, because what you get in the model is, if you look back at this index function, we're going to be estimating that beta 0 and that beta 1. The beta 1 tells us how things like x relate to the index function. which has to go through a transformation to turn into something that we are actually interested in, the probability that the dependent variable is equal to 1. Interpreting the index function is hard to do. So instead what we tend to do is something called, we get marginal effects. And what the marginal effect is it says, let's take those x's, let's change them all by a unit, let's see what changes about the predicted probabilities, and then we will report that. Which puts the effect of x back in terms of the probability of y, just like a linear probability model would do, much easier to interpret. So instead of saying a 1 unit increase in x increases the index by 2.2 units, and you're like, what does that mean? Instead, you can say something like a 1 unit increase in x changes the probability that y is equal to 1 by 2 percentage points, right? That's a lot easier to get. Now, getting these average marginal effects is difficult because if we look back at our graph, the marginal effect, which is the slope on that line, is different at every point on the x-axis. So there is no single marginal effect. Everybody's going to have their own marginal effect depending on where they are on that x-axis. So there are a number of ways to take everybody's individual marginal effect and aggregate them together to get a single value that you can report. The one that I recommend is called the average marginal effect, which is this. You look at all those data points on the entire graph. You calculate their marginal effect for each individual. So basically, for each data point, you look at the slope of the logit line at that point. Then you simply take the average, and that is the average marginal effect. You can get the standard error on that. You can see if it's statistically significantly different from 0, all that good stuff. There are other ways to calculate marginal effects and aggregate them together, but that is one that I think makes the most sense. Because it allows each individual person's marginal effect to be averaged together to get your average marginal effect, which I think is typically what people want out of the whole thing. All right, so that was a very brief overview of logit and probit modeling. It is a very even briefer overview of the whole world of nonlinear modeling more broadly. It's not really a focus in this book because when we're thinking about causal inference and research design, really we want to think about that research design first, and this is more of a detail of estimation. And so I leave it largely to other books, although there is some more technical detail in the textbook itself if you want to check that out first. Now, in the next set of videos, we're going to be moving on from the regression chapter finally. In particular, we're going to be getting into a different way of being able to control for variables, which is using matching. So I'm looking forward to that. Thank you.